we're going to be looking at a different style of proof. This style of proof is mathematical induction. With that being said, when you're looking at this type of proof, you are showing there's different steps here. The first step is to show P1 is true. The second step is to show that P of k plus 1, which is the previous term, is true for the different formula that's given. Not previous term, next term. And this is all based on a given sequence. Okay, so it's a lot of math jargon right there, but it's a little bit easier to kind of figure out how to break everything down based on an example. So let's jump right into that. So the first example, let's say that I have 5 plus 7 plus n plus 11 plus ... It comes out as a formula of 2n plus 3, which I'm going to tell you now. So that 2n plus 3 is where I'm going. I could also have a formula of n plus 4. Okay, so what I'm going to do here with mathematical induction is I'm going to show that 2n plus 3 is the same thing as that n plus 4 when I'm looking at my next term. Okay, so your first thing that you want to do is you want to prove that P1 is actually true, because if it's not, you can already stop your mathematical induction proof because it's not going to work. So when I do this, P of 1 represents when n equals 1. It's the first term of our sequence. So I'm trying to show, okay, using those formulas, that in fact, I will get 5. Okay, so when you do this, you're plugging it into the right side. So we have 1 going into the n spot, 1 plus 4. Okay, that equals 1 times 5 equals 5. Check. Because that 5 from the very beginning of our sequence is there as well. That's our first term. So we are good to go on our anchor, is what they like to call it. P1 is true. Okay. The next step is to actually figure this out and make sure that it in fact works for the next term and the next term after that. Okay. So when we do this, we're taking that k plus 1 and we're substituting it into both sides to show that we can get the same thing. So we add, in this situation, we add 2 times k plus 1 plus 3. And the reason why is because that came from here. And we're just adding that next term, that k plus 1. Because if k is 1, which means that it's the first term, if I add a 1, that would be the second term. That's the next term. Like I keep using those terminologies over and over. Okay, so when I say both sides here, what I mean is we have that 5 plus 7 plus 9, ... I know there's an 11 in there, but just moving on here. So we're adding that on to both sides. Of our equation, okay? When we add it on to both sides of our equation, we will now be working with the right side exclusively here. And when I get this broken down a little bit, I'll have to explain why I know it's true. So when you're working with that right side, first thing I see is I see a lot of distribution. So I'm going to go ahead and distribute that information. And I am now going to combine my like terms. K squared plus 6k plus 5. Well, It's in the form of a square. It's a quadratic. I bet you I could AC factor that. Boy, that AC factoring comes back a lot. If I AC factor that, I get k plus 1, k plus 5. This is the end of this, and let me explain why. So the original statement, was k plus 4, right? So we're supposed to find this for the next previous term. So if I'm supposed to find that for the next previous term, these k's here are supposed to be plus 1. That worked out for that one. Check, check. K plus 1 plus 4. That does in fact work out. So that's how I know that I am done at the end of this proof. Okay. So technically, actually, if you want to know the ending of a proof, you put a box behind it at the end, and that's telling you you're done. So that is in fact our proof, because that k plus 1 was replaced, and when we simplified it down and added that 2k plus 1 plus 3 to both sides, it did in fact work out to be the plus 1 version of the original formula. Kind of tricky, I understand. Let's deal a little bit more specifically with sequences and how this relates to what we're doing, okay? And why this is tied in with sequences and series and that kind of information. So let's say that I have an and an minus 1 plus 5. Okay, so this given to me, actually, this is a recursive formula. Okay, because I'm given my A1 and I'm being told that the previous term plus 5. Okay, recursive formula, no questions asked. We've dealt with this. It's an arithmetic sequence. Okay, so if I rewrite this in explicit form, I could then work through and prove that it in fact, you know, by a mathematical induction is the correct formula or the correct rule. So when we're doing that, we're going to rewrite this into explicit form. Piece of cake, because we already know the arithmetic form is in this format with this formula. Okay, so I could multiply this out a little bit and get it reduced down. I now have a rule. Just like we had a rule in this last example that circled here, that 2n plus 3, I now have that rule. It's 5n minus 2. Okay, well, I'm doing the same thing then. I'm proving it using mathematical induction. Just looks a little different because I don't have that you know, 7 plus 9 plus blah, blah, blah in front of it. And that's okay. Step 1, prove P1 is true. Okay, so we take our 1 and plug it into that formula. 5 times 1 minus 2 equals 3. Check. Because it equaled 3 up there. We were told it was supposed to equal 3, and we in fact proved it with our rule. Okay. Step 2, our original. Our original is 5k minus 2. Okay. But we're supposed to, if you notice here, if you look at this, right here, this is the original, and we're supposed to add 5. Okay. So now, that's supposed to equal our k plus 1 side. So we will have 5 times k plus 1 minus 2. So we just need to go through and actually simplify this and show that the original formula of that previous term, plus 5, equals when we plug in that k plus 1. Okay, so 5k minus 2 plus 5 ends up being 5k plus 3. No questions asked. Over here on the right side, I've got 5k plus 5 minus 2. Looks pretty darn similar. Check. So there is our proof. We are done. I make my box, I fill it in. So you're just going through, even though it looks kind of scary, it's not that bad. You're just taking that k plus 1 and substituting it in, distributing it and combining like terms. You might have to factor just to show that the previous term does in fact work out for that formula. Again, this is our tie to our recursive formula to our explicit when we're dealing with how does this fit into our unit here. Most of this stuff isn't geometric. Geometric if we're talking about an actual formula that's got multiplication in it, but it's a little bit different than the geometric sequence formulas we've been using. But anyway, that is mathematical induction. You're just taking something, proving it true, and then finding the previous term with a k plus 1.